Tonight we're going to talk about intern and mixture designs. We've been talking throughout the semester about designed experiments, and I don't want you to miss out on this particular kind of designed experiments because I didn't know about this for a long time. So my bachelor's degree is chemical engineering, and I went through school, didn't have any experimental design exposure until I started working. Then we learned about Taguchi methods. We talked about those and the deficiencies a little bit. And here I'm working in a job that involves putting different ingredients together to make different kinds of synthetic rubber for different applications. So it needs to do different kinds of things. And so can I have well, I guess I'll just show you guys. So you can make rubber. Do these look about the same? Mm-hmm. Approximately. Okay, so I'm going to bounce this one, see what happens. Woo! It's bouncy. All right, would you expect this one to do the same? They look the same, right? All right, let's see.
No.
Oh, sometimes it just goes flat, doesn't bounce at all. So it is not as bouncy. So whenever we are mixing different ingredients together, we can get different kinds of results. And this is the kind of situation where we want to use a mixture design because the amount of one ingredient, as we change that, it affects the proportions of the other ingredients in the mixture. And so I'll tell you more about that and different options that we have. But that's what we're going to talk about today. Because I don't want you guys to graduate and not know about this tool. And if you're working with other engineers who may have never heard about this, you're in a position to direct them toward the right kind of tool to help them experiment most efficiently, to get the most information out of the resources they're putting into their research. So what do I want you to know in this short time? I want you to know, when do you use a mixture design? What type of mixture design might fit your needs? How can you create that design using software? And how would you interpret the results? So it's going to be really practical today. In another lesson, we might get into more of the mathematical modeling and some of the deeper statistical stuff, but this is what I really want you to walk away with, is the practical stuff. So we'll be walking through the answers to those questions. Part of what got me excited more recently about mixture designs, when I first learned about them in my PhD study, I'm like, this is amazing, how did I never know about this? But I've been watching, does anybody know who this guy is?
Mark Rober.
Mark Rober, okay. And how do you know about Mark Rober?
He's YouTube.
On YouTube, okay. That's how I've learned about him too. A friend of mine told me about this like squirrel obstacle course, and my kids and I had to watch it, and we watched several of his videos. He has one video from 2019 where he wanted to set the world record for elephant toothpaste. And so they wanted to play in this. So they had a safe concoction mixture that they used so they could do that. Instead of using some harsher chemicals, they used the yeast mixture. But you can see the swimming pool here was filled with ingredients that as it reacted, it foamed up and it oozed over the sides and got the world record. Well, this concoction is a mixture. It's pretty small, but this is the recipe. So the main ingredients are hydrogen peroxide, dry yeast, warm water, dishwashing soap, food coloring. And then just the safety equipment, safety goggles, the container to put it in, etc. So we're going to combine different amounts of these ingredients to create the mixture. Well, not satisfied to lose his world record in 2019 pretty quickly, he wanted to make something a little bit more, I don't know, bigger. And so he began experimenting. And so this is his devil's toothpaste video from 2020. And as he's going through the 20-ish minute video, he talks about running over 150 tests. And he talks about different factors that he's testing. So one of the factors is looking at the scaled up neck dimensions. He wants to use an Erlenmeyer flask to direct the kind of eruption up, straight up, and to create some kind of laminar style flow where it's not all just like confetti and it's not all just like ooze. So finding that point with this being one of the factors, the neck length, different dimensions for the neck length. They tested that at different factors, 22 inches, 33 inches, 55 inches. And he talked about what happens when you vary the soap amount. And so this is my screenshot of the video of that with different levels of the soap, different amounts of the soap. The soap is part of the recipe, and so it's part of the mixture. And you can see how he's measuring the height with these different levels of soap. And he also looks at different food coloring. So those are going to be set factors for the food coloring. Everything here we could address with a normal fractional factorial design. But the dish soap is part of the mixture. And so as I'm watching this, I'm like, oh, I don't know if Mark Rober knows about experimental design, because here's a screenshot from the video, and he has test 1 through 10, and he's varying milliliters of something, and he has a measurement of height as the response variable. And he's got some ratio here that I'm not quite sure what it is. But as he's doing that, I'm like, oh, please cringe with me. It really looks like he's doing one factor at a time experimentation, which is what we're all taught in school unless we're taking this class, or maybe a class in the statistics department, to know about how we can experiment a little bit more efficiently with these methods and models. So I'll tell you guys, I told my kids, I'm like, I need to write Mark Rober a note and ask if he knows about designed experiments in a very respectful way, because he worked for NASA, right? And so I put off writing the note. They kept asking me, is Mark Rober going to come? I said, I haven't written the note yet. I finally write the note, copy myself. It goes to my spam folder. So it probably went to his spam folder too. And I thought, oh, that must be how it was supposed to be, because he worked for NASA. And the only person I know that worked for NASA is a Lean Six Sigma black belt. And so I think, it's NASA. Surely everyone is trained in design experiments, because this is one of the first things when I worked for Intel. They had, for my 10-week internship, we had to take a course on design experiments. So surely everyone at NASA knows. Well, this fall I went to a conference and met an incredibly brilliant NASA engineer who has a statistics background. And in the presentation that he gave, he let us know that NASA projects are not required to involve statisticians. So it is completely possible to have a graduate degree in engineering, not know that it might be beneficial to reach out to the statistics group and have them kind of help guide some of your testing and research. So it is possible that he doesn't know. So I might try the email again. But he did have good results. He went on and came up with a great way to earn the next world record for Devil's toothpaste, the highest. And then he was even more challenged. You can see how it's exploding off its foundation here. And so a year later, no? Okay. He tried again, over-engineered the Erlenmeyer flask, and it went even higher. So he got some good results even without using design of experiments, but I just think he's missing out, and I think he'd be a great spokesman for this tool if we could just get him on our team. But what are mixture experiments? I've kind of given us a little bit of an idea. There are special types of response surface designs that we've talked about a little bit. The goal is to figure out what blend of ingredients is going to give us the best result for what we want to measure. Maybe that's ooey gooey cheesiness on our pizza, or maybe that's the lightest, airiest cake with different ingredients. Well, but if we talk about cake baking as an example, again, if we're looking at what settings are which, if we want to test our different bake time and temperature, what's the optimal time and temperature to bake the cake to get the best moisture, if that's moisture content is our response, then we can say, hey, I'm going to bake it for 20 minutes at different temperatures at 300, at 350, at 400, 450, and see what happens, what starts burning. Or I could just keep the temperature the same and vary the time and see what kind of responses we have. And we can set up that experiment. They're not dependent upon each other, the time and the temperature. You can change one without it affecting the other. But if we work with ingredients, if we add more flour, there's a greater proportion of flour. There's less of the other ingredients in the mixture itself. And so we've got this little graphic here. Friends don't let friends use factorial designs for mixtures. So I want you guys to remember that. There's different types of mixture designs. And the type that you use is going to be kind of dependent upon your situation. There are simplex designs, and I'll talk a little bit more about those. They're used to study the effects of mixtures on the response variables. These all are. There's two different kinds. There's the simplex lattice and the simplex centroid. There's also extreme vertices, optimal designs, and space filling designs. These are all options in the software, so I'm going to just go through it a little bit, and then we'll look at an example using one of them. Simplex designs, and I have this slide, but I think it's going to make more sense if I draw it. Let's say we have 3 components. And at one point, it'll be 0, and at one point, it will be 1, and there are different proportions. If we want to check, let's say, 2 different settings. So like 0, 1/2, and 1, 1/2, and 1, 1/2, and 1. This is going to be what it's going to look like for our design. We're going to have this many points, 1, 2, 3, 4, 5, 6. And so if we have them, you could say it's 1, 0, 0, because it has to add up to 100, or 100%. And we could have 0, 1, 0, 0, 0, 1, 1/2, 1/2, 0, 0, 1/2, 1/2, and 1/2, 0, 1/2. So we would set these up, we would get our response for those runs. We would randomize this, we would probably want replicates, but this is the basic simplex lattice design. Now, one of the deficiencies of this is that if we want to know anything here in the middle, we have not put any kind of experiment there. So the big change that there is with the simplex centroid design is it's going to add a center point, so that we have a little bit of information in there about what's happening in the middle, and that's going to be where everything is 1/3. Where everything's equal. And if we had 4 components, we would make this into like a pyramid, and it would be the same kind of thing. So those are the simplex designs, briefly. And here are some pictures that show kind of what I drew on the board. I don't know that there's anything really to add to that. You can also augment the simplex design. Let's say you want a little bit more information. Augmenting, we've talked about that before. If you want to augment to get more information outside of the cube of the design space that we've talked about in previous classes. So if we wanted to know more, we could just have our center point, and what else did they add? They added a point here. I'll use red. And here, to give us more information inside the triangle, to have a little bit better feel for things. Right, for optimal designs, I watched a video by a software company, and they said, usually this is what they're seeing in real life is the need to use optimal designs. Why? Well, let's take a look. If we have, I might have this on a slide, but let's say we have our 3 factors, but we know that for whatever reason, x1 can't be any greater than this 0.5. So in that case, maybe that's cut off entirely there. And maybe x2 can only work in this range. So maybe we also have to cut off this and this. So now, if we were looking at a regular design like I have here, a lot of that space along those outside edges isn't going to tell us anything useful because we can't even use that. So optimal designs are going to be more ideal when you have these kinds of constraints. And the software will help you set this up. But if you've got some kind of limited design space, then you're going to want to go with an optimal design that will handle that. Now, yeah. You can kind of see in this smaller triangle, that's the, given the constraints over there. If the constraints for A1 are 0.2, it has to be between 0.2 and 0.8. So you can see that here, just a limited design space. Another approach is space filling designs, and this is kind of a newer approach, and here you can let the software jump will do this. I don't know if Minitab won't do this. Minitab, from what I could find out, will do the simplex kinds of designs, not the optimal. I could be wrong on that, but that's what I was finding out for this. But it will tell you, here are all of the runs, and the numbers are very small here, but they're all over the design space. So if we were going to draw that in here, it might look like something like this, just kind of like evenly spread out throughout whatever constraint set you have. And just kind of set up through a different algorithm to figure out what the spaces need to be. So it gave us 30 runs, we could change that, but it's just another option. So let's look at an example to think about how this works in real life. And I guess this is a pretty classic example because I found it in one textbook, and then I found it on another internet example, another citation. It's from Cornell's book. I found an old copy, Experiments with Mixtures. So I've got this for reference if anybody wants to do some deeper reading. I got to hear him give a talk about the history of mixture experiments. And if you all can imagine on transparencies and an overhead projector when that wasn't really a common thing anymore. It was just really fun to hear him talk about that. This example is looking at 3 different kinds of man-made fiber put together with the goal of making strong draperies. I don't know if anybody really knows much about drapes anymore, but in this example, they want the fabric to be strong. And so what they're measuring as they combine these different components is the strength it's going to take to break them apart. And so if you can see this machine here in the corner, this is what they're testing. They're going to pull it apart and measure that tensile strength in kilograms that it takes to break it. And they want it to be a really strong fabric. And because, I don't know, do you guys like yarn? Anyone? I brought some examples of yarn because I like yarn. As far as like these different blends go, different blends have different properties. So I'll pass this around. This is 100% wool. And you can kind of feel it, and Think about how fuzzy it is, how soft it is. This is 100% acrylic, a man-made fiber. Wool is a natural fiber. I have another 100% acrylic that's a little bit different. It says it's anti-pilling, so I don't know if they do that with the material or if they do that more with the twisting, etc. And then this yarn is a blend. It's 80% acrylic, 20% wool. So you felt the wool, there's different kinds of wool, and then this is a blend of wool and acrylic. So you can kind of see some of the differences, and you can think about what would be maybe important if you were creating something. Would you want it to be warm? Would you want it to be soft? Would you want it to not pill, which is making those little annoying balls on the fabric? Here they're testing for strength, but they want to find out what's the optimal blend, and you can kind of think about if you were creating with a material, kind of what you might choose. We're going to put that together as a mixture design to test which of those materials are going to be most effective in giving it the strongest fabric. And in JUMP, I want to walk you through the screenshots. If I had my computer with me, we would walk it through step by step, but I can show you kind of how it would work. So we go to DOE, Design Experiments, here in Classical, go to Mixture Design, and that's going to pull up this screen over here. And it's probably a little hard to see over there. Here are our options. We can put in our factors, and then we've got optimal design, simplex centroid, simple lattice, extreme vertices, A, B, C, D, which we didn't talk about. That's for factor screening a little bit more, and space filling designs. And you can set your number of runs. For this example, we'll look at simple lattice. The default here is the number of levels is 5, but we're just going to look at 2. We're going to keep this experiment simple. Maybe we don't have a big budget to just learn a little bit, or maybe we'll find out everything we need. Once we do that, I've gone ahead and programmed in the names of our materials: polyethylene, polystyrene, and polypropylene. We have our runs, the 0, 0, 1, 0, half, half, 0, 1, 0, and so on, like I put on the board. And we've got one replicate, and that's going to generate our list here of 12 runs. The example gives 3 data points for all of the lines that include 1/2. So if it's part way, they did 3 runs. So I added those in since we have those data. And so that's why I have 15 here. Once we have run the experiment, gotten the data for the response variable, then we're just going to look at coming to analyze and fit the model. We'll say this is our Y, the observed elongation value, and we'll hit run. And that's going to give us this cool output here. So we can check our residuals, make sure everything's looking good here, kind of no pattern for the residual by predicted. We're looking at the studentized residuals, making sure they're kind of within these bounds that are given. We can see real quickly our key values for what's significant or not. The actual by predicted plot up at the top, the red line will be the predicted equation. The black dots are the actual values that we got. And we can see that, yeah, that looks pretty well aligned. And if we would scroll down, we get to the best part. We get to our parameter estimates here that tell us how big of an impact is this having. And you'll notice we've got our 2-way interactions. So where we tested those halfway points, we can see, well, what's the interaction between polyethylene and polystyrene, all of those 3 combined. And so we've got our estimates here for our equation that we might talk more about next time. And we got the prediction profiler. Now, this is about the coolest thing, and we've talked about it a little bit with response surface, but you can actually move these lines around. So on this, I can see polypropylene is my highest positive coefficient, polypropylene. So I want to maximize my use of that. So I can drag this red line over to where this curve is going up. And as I do that, all these others will change because as we have more polypropylene, we're going to have less of the other substances. Polystyrene isn't helpful, and it's kind of taking away. So if we set that to 0, and then we have this other parabola, we can optimize that and get to the point where if we have about 0.3, about 30% polyethylene and 70% polypropylene, that'll give us over 17 kilograms force, the strongest we can really do with what we have here. There's also a mixture profiler in JUMP, and so it's just another tool, kind of shows us the same kind of thing. You can have it set where you want different contours. So at 17, it kind of curves like this. At 16, it's here. As you get to smaller numbers, it starts to move like you can maybe see over here with the curve around this corner of the triangle and the curve at the top. So you can kind of play with that. You can set the contours to see where they are. You can move this around to see what different proportions give you what kind of response with that prediction equation. So some tips and tricks to remember if we are recommending mixture designs or if we're using them ourselves. If you're working with a mixture, don't use factorial designs. Doing replicates is going to be critical. We've talked about that with other designed experiments as well. Optimal designs are going to be more flexible and more practical in a lot of cases. We're going to have, we're not going to have this perfect world in a lot of the things that we need to test and check. So we're going to need to be able to work with those constraints. And so optimal designs give us a good way to do that. When I was watching the video on Design Expert, it said to not convert to ratios. I find converting to the ratios is kind of confusing, but JUMP is the software that I have available right now. And Design Expert looks better, but I don't have it. So if you work with Design Expert, instead of these zeros and ones, you can say, hey, these are my actual values. It's 1 to 5. And this other variable I can have from 2 to 17, or whatever your real values are, and not have to convert to ratios. In JUMP, you do. So I guess it kind of depends on the software you have available. It's more ideal to not have to take that step, because it sounds like it's just kind of a pain. Put a lot of thought into what you want to test and how you're going to measure it. Now, textbook example, it's already set up for us, measure hardness with tensile strength, no problem. But what if we want to measure softness of the yarn? What I think is soft might be different than what you think is soft. And so we've got to figure out what's our measurement system that's going to best evaluate this in a consistent kind of way. Soft is kind of, subjective. If we're looking at ooey gooey pizza cheese, we might have to figure out, okay, do we evaluate that based on how much it will stretch? How do we have a taste testing panel that tries different pizzas? We've got to figure that out. How can we have a good measurement system for the response, and what are the components are? What are the realities of those limitations, those constraints as we set up the experiment? We got to make sure that we're testing in the right space. So again, if we're running these points along the outside of the triangle, but that's not where we can really operate, then that's going to be a waste. So we want to make sure. And we want to see if we can work to master building optimal designs, because those will be what's probably most practical and applicable in industry. So as we close, I want you to think about an opportunity to make your own mixture design. So I've got here different recipes for pancakes and different ingredients. Everything uses flour. Everything here uses baking powder. I put this up because a friend of mine teaches culinary arts in Nebraska, and she said she was giving her students an experiment. Start with flour and water or milk and make pancakes. And then add baking powder, see what happens. Then add an egg, see what happens. Add oil, see what happens. So I love that she's bringing science and experimentation into the kitchen, but I wonder if we could do that more efficiently by making a designed experiment. So I want you to be thinking about, before our next class, how you might do an experiment to optimize pancakes. You might have different constraints. You might have someone in your family who can't have eggs. You might have someone who can't have gluten, so maybe you look at even a non-flour, non-wheat flour option. You might think about what makes a good pancake, because I found a recipe for these Russian blinis. They're like little crepes, super thin. So if you want light, fluffy, thick pancakes, it's going to be a different kind of mixture than if you want a flat, skinny pancake that you wrap up some deliciousness in or something like that. So I want you to be thinking about what your metric would be to evaluate a good pancake. And that might be different for most of you. What would you evaluate? What ingredients and how could you set up a mixture experiment? And so we'll start our class with a discussion on that next time we're together. So thank you for your kind attention, and I'll see you next time.